As you can see from this graph, it's so the green part is what's inside the green boxes are things about. Oops. So the green boxes results problems in projection theory, and the blue boxes theorems results in projection theorems in geometric measure theory. So hopefully can discuss some of the boxes and discuss their connections. So we'll start with restriction theory. Josh already made a very nice introduction in the first lecture. So restriction theory is about studying the functions whose Fourier transform is supported on some manifold M in Rn. So the question is, what can we say about the size of F? What is the LP norm of F for some P greater or equal than 2, for example? So we will start with say that if M is a hyperplane, let's say it's the hyperplane where the last coordinate equals to 0, and then this Fx can be written as e to the 2 pi I x dot product with c comma 0 and fc dc. So this is a function with Fourier transform supported on this hyperplane. Then we can see that the f is invariant for the on the last coordinates. So if f is supported on the hyperplane of flat M, then we can see from this example that the LP norm of f is unbounded because it's it's invariant on the last coordinate. So then the problem becomes more interesting when M is curved. So here are some examples when f has Fourier transform supported on the paraboloid, and such function is related to problems in PDE. So this is a solution to linear Schrodinger equation. And then there is a second example when f has Fourier transform supported on this moment curve, which is related to number theory. So Josh already talked about it in the first lecture. In restriction theory, the central open problem is Eli Stein's restriction conjecture says that if f has Fourier transform supported on the paraboloid, and this P means paraboloid. So this function has Fourier transform supported on the paraboloid, then the LP norm for any P greater than 2n over n minus 1 is bounded by some constant times the LP norm of its Fourier transform. So this critical exponent 2n over n minus 1 comes from the function where small f equals to 1. So this is the formula of the function with Fourier transform supported on the paraboloid, and then the Fourier transform of f is related to this small f. So also in Josh's talk, he says that we can show that Stein's restriction conjecture implies the Kakeya conjecture. So in fact, so this range, so P greater than some number, so when if one can show the restriction conjecture holds P for P greater than 2n over n minus 1, then one can show that any Kakeya set in Rn has Hausdorff dimension n. But as long as we can show some range of P, let's say P greater than something, and this range will correspond to a certain dimension of the Kakeya set. So even partial progress on the Stein's restriction conjecture would imply some partial result on the Kakeya conjecture. But usually the implication goes the other way, means that one usually needs to understand very well the Kakan set in order to make some progress on the size restriction conjecture. So also, as Josh talked about in his first talk, the way restriction conjecture is related to Kakan set conjecture is via the wave packet decomposition introduced by Jean Bourgain in the 1990s. So in a large ball of radius r, for function f with Fourier transform, so this is where the Fourier transform lives, supported on the paraboloid, one can decompose such f into a sum over wave packet. And each wave packet, ft, is essentially supported on one of those long skinny tube. And also the absolute value of ft is essentially constant on one of the on the support. So this means that each ft is rather easy to understand, and in order to understand f, we need to understand how their essential support overlap. So understand how those tubes overlap, and also at the place when they overlap, one needs to understand how the oscillation. So here I don't know if you can see the color, but so supported the Fourier transform of f is supported on the paraboloid, and we can decompose the paraboloid into small caps of radius r to the minus a half. The reason is because suppose we only care about the function supported, the function on the large ball of radius r, then each of those small cap will correspond to those tubes. I made them the same color, pointing in so the tubes pointing in the direction of the normal direction of the cap. So, and each cap might correspond to several parallel tubes, and different cap corresponds to tubes pointing in different direction. And this is where the curvature comes in, because we have different normal directions, so we have tubes pointing in different directions. This is just a review of what Josh talked about on the first talk. And so in 2014, Bourgain and Demeter made a big progress in the field. They proved this Bourgain-Demeter decoupling. This is so size restriction conjecture estimates the LP norm of f by the LP norm of its Fourier transform. Bourgain-Demeter decoupling, well, decoupling inequality was first introduced by Tom Wolfe in 1990s. Bourgain and Demeter, they proved sharp decoupling inequalities. This provided a different way of understanding the LP norm of f. So let's give the caps a name tau. Usually we name the caps theta, but I'm going to use theta to denote direction when we talk about projection theories, and rename it as tau. And f tau just means we take the Fourier transform, which has support on this paraboloid, and then we restrict the support on tau. So in reality, there should be a partition of unity, but for the sake of presentation, I will just say that this is restrict on tau. And so f tau is Fourier restrict on this tau. Bourgain and Demeter showed that for any p between 2 and certain number 2 times n plus 1 over n minus 1, the LP norm of f in a big ball is bounded by the little L2 sum of LP norm of f tau. So this just means some weight function that essentially the characteristic function of BR, but has some rapidly decayed tail. Of course, you can also try to imagine that this is just BR. This is useful because usually the right-hand side, f tau, is rather easy to understand. So here is an example. Suppose, let's say f tau is supported on just one point. Then one typical example in the application of f tau is just e to the 2 pi I y some phase times x. So in other words, this integral on BR, just the volume of BR to the 1 over P. Later there, Bourgain and Demeter and Guth proved also sharp decoupling inequality for functions with Fourier transform supported on the moment curve, which has application, implies Wiener-Goldorff's mean value theorem in number theory. Those two decoupling inequalities has been very powerful in studying different problems in harmonic analysis, MPDE, and number theory. So the range of P, this number, just is another way to sort of explore the curvature. So maybe I'm going a little too fast. This is a very fast introduction to what has been exciting in restriction theory. Are there any questions? Okay. And now we can talk about projection theory, and later we'll talk about their interactions. So I'm going to go slower in projection theory. So let's have a warm-up. Suppose theta is just one direction in a plane. Theta is in S1, and pi theta is this orthogonal projection to the line in direction theta. So here is the picture. Let's say E is those points, and those directions are theta, and those points are the projection image pi theta E. So the question, the warm-up question we want to study is: suppose we have a set of directions in the plane, and we also have a Borel set E in the plane. Can we find a direction in our set of directions such that the Hausdorff dimension of the orthogonal projection image is large? So there is classical Mastrom's projection theorem says that, well, if we allow for almost every direction, the projection, the orthogonal projection preserves the dimension or achieves the maximal possible dimension. So since pi theta is a Lipschitz map, so this cannot really increase the dimension. So this is a sharp bound. But Mastrom's projection theorem is powerful, but it requires a lot of directions. So one might ask, what happens when lambda is, the set of directions is small? This is proved by Jean Bourgain. Bourgain's projection theorem, where he shows that as long as the Hausdorff dimensions of the set of directions are positive, then one could have an epsilon improvement. Sorry, when I say epsilon improvement, first of all, this greater or equal than the Hausdorff dimension of E over 2 is a much easier bound, but having this epsilon improvement is highly non-trivial. And this is the key theorem that has been crucial in developments in harmonic analysis and also some dynamics problem. So this epsilon depends on the dimension of lambda and the dimension of E. Also, this consequences of Bourgain's projection theorem was also used in the proof of the Kakia set conjecture in R3. So also this is a theorem that distinguish real numbers and complex numbers. For example, we can take, let's say, suppose we are not in R2, but we are in C2. So then we take E to be R2 to be a subset of C2. Then we can just take lambda to be S1, which is a subset of CP1. That's but then we know that for any theta in lambda, pi theta E has Hausdorff dimension equals to 1/2 of times the Hausdorff dimension of E. So for this, so this says that in C2 this theorem is not true. So one might ask, so this is just an epsilon improvement. So you could ask, what is the best possible bound? This was the best possible bound is so except those extremal terms, the best possible bound is this epsilon should be the dimension, a Hausdorff dimension of the set of directions over 2. And this was proved as a special case of the Furstenberg set estimated in the plane that we are going to discuss in the end. So this is what we know for the planar case. Are there any questions so far? Okay, so for the general setup, suppose we have an m-dimensional subspace V, and we let pi V denote the orthogonal projection from Rn to this m-dimensional subspace. Now the analog question is, suppose we have a subset of the Grassmannian, or in other words, a collection of m-dimensional subspaces in Rn, and can we find a subspace in this collection such that the Hausdorff dimension of the orthogonal projection image is large? So the first observation is that it depends on the curvature of lambda. And this goes back to the theme that a restriction theory is about the curvature of the Fourier support. And then when we talk about those orthogonal projection problem in higher dimensions, we also have to consider the so-called curvature of the collection of m-dimensional subspaces. So what does it mean? So here is an enemy example. Let's say let L be a line, so this is a line in R3, and we consider lambda to be the set of directions that's orthogonal to L, so this is our lambda. If E is contained in this line, then for any theta in our collection lambda, the pi theta E is just going to be 1 point because it's orthogonal. So this means that the Hausdorff dimension of the projection image is 0, and this is a bad example. But this example has some structure, and also the lambda is quite flat, so it's a great circle. And so Fassler, an opponent, asked in 2013 that what happens if lambda is a curve, let's say smooth. In fact, C2 is enough, but let's say smooth curve away from any great circle. For example, we can take a small circle. It turns out that we could have, for lambda, let's say that's away from any great circle, the Hausdorff dimension of the projection image equals to the minimum of the Hausdorff dimension of E and 1. So this is like the Mastrong type theorem. It preserves the dimension or attains the maximal dimension. So recall that for the classical Mastrong's projection theorem, even though we stated in the planar case, but it also generalized to a higher dimension. So an analog of Mastrong's projection theorem in R3 says the following: for almost every direction theta here, then the projection image has the Hausdorff dimension of the projection image equals to the minimum of the Hausdorff dimension of E and 1. But for the classical Mastrong's projection theorem, we require is true for almost every for almost every direction in the sphere. So we need to have access to almost all directions. But the strength of this theorem is that we only need to consider what happens on this curve or on this small circle. Then we know that for almost every direction on the small circle, then we have an equally good projection bound. And this theorem was first proved for the small circle case by Ken Markey, Opponen, and Venuri, and also for the general C2 curve case by Pramanik, Yang, and Josh Zhao, and where they use some method that's developed by Tom Wolfe on estimating this curve tangencies, and also independently by Shen Wengan, Larry Guth, and Dominique Mardac, where they use high-low method that we are going to discuss next. So this is for we call them restricted projections because we restrict our attention to a curve on the sphere, and this restricted projection problem also generalizes to higher dimensions. So we proved the following. This also uses the so-called high-low method and decoupling. So in higher dimensions, suppose gamma is a non-degenerate curve. A good example of gamma can be gamma t is equals to the moment curve. And we say non-degenerate if the derivative of if the determinant of the first until the nth derivatives is non-zero. So in particular, this moment curve satisfies this non-degeneracy condition. And so here, let m be some number between 1 and n minus 1. For any t for any point in the curve, we can define the m-dimensional subspace VTM as the span of its first mth derivatives. And we can also define the orthogonal projection PT from Rn to the subspace spanned by the first m derivatives. Then we also have this Marchand type estimate. So for almost every t, so for almost every point in the parameter, the Hausdorff dimension of the projection image equals to the minimum of the Hausdorff dimension of E and M. So the strength of this theorem is again, so here when we let lambda be the set of the subspaces, then lambda is a curve in the Grassmannian, on the Grassmannian, and it's only a curve. So the analog of Marchand's projection theorem says that for almost every m-dimensional subspace in Rn, but here we have access only to a curve. So the theorem says that for almost every subspace parameterized by some point on the curve, we have an equally good projection estimate. This theorem, the proof of this theorem is using the high-low method in Fourier analysis and also using restriction theory. So we are going to talk a little bit about this high-low method. So this is an example of how restriction theory is applied to projection problems. Maybe I should pause and ask if are there any questions on this, the statement of the theorem?
Sorry, the theorem above there is true for all m and n, or?
This is true for all m and n, for all dimension n and all m between 1 and n minus 1. Yes, yes. Are there more questions? Okay, so I'm just, even though this is a general audience talk, I still want to talk a little bit about proof ideas. But this is hopefully not too difficult, and even if it's too difficult, it only lasts for one slide. So as in the first few talks, in the first previous talks, we usually consider some like delta thickening of the geometric object. So now instead of considering a t-dimensional, a fractal set in Rn, we can consider E to be a set of delta balls. So E is here. We want to say that we want to show the projection image is large. So there is a natural way to study the projection, to try to understand the projection image. So let's say in the special case of m equals to 1. So in other words, we project to the line in direction of gamma prime t. So for this set, the projection image is just those yellow dots, those yellow balls. How to understand it? So let omega t be delta times 1 times 1, so the delta neighborhood of hyperplanes, we call them slabs S, that's perpendicular to the line that we are projecting to, and also that intersects E. So we only care about those slabs that intersect E. And it turns out that the projection image has about the same size or cardinality as the number of slabs required to cover E. So here in this picture, we let's say the E project to this line to 3 more balls, then this means that we require 3 slabs that's normal to this line to cover E. So to show that the projection image has large dimension can be rephrased as follows. For each direction gamma prime t, there might be some other directions, we use some slabs that's normal to this direction to cover our set. And we want to show that we need a lot of slabs to cover it. So this means that for one of the direction, the projection image should be large. So how do we show that we need a lot of slabs to cover it? So we can define a function f to be sum over, you could think this as characteristic functions of those slabs. But in reality, because we want to use Fourier analysis, we use a smooth bump function on S, on the slabs S, but characteristic function is also a good model. And we want to study the integral of f on E, and hopefully we can show that the LP norm of f is small. So what does this mean is that let me see. So after we can do the Hausdorff inequality, this is bounded by the size of E to some power, and then the LP norm of F, 1 over P. So if this is bounded by something, then it says that sorry, Yeah. So after Hausdorff's inequality, if one can show that, in fact, this is not saying that LP number F is small. It's like, hopefully you can show that this is bounded by some quantity times the number of slabs. And then using Hausdorff's inequality as before, if we can show that this is bounded by some powers of E times the LP num of F to the 1 over P. So, and this term we could understand it well by double counting. And if this is bounded by something about the number of slabs, then in the end we can show that the number of slabs should be large. So this would show that the projection image is large. So I hope I have more or less convinced you that this is some bound, some estimate we aim at. And how do we do it? I will just say quickly how this is related to restriction theory. So phi s is a smooth bound function on S, and then we analyze the Fourier transform of phi s. So it is essentially supported on the tube that's orthogonal to the slab S. And we already know that the slab S is orthogonal to the line pointing in direction gamma prime t. And so we know that the Fourier transform of phi s is supported on the tube pointing in the direction gamma prime t. And now the Fourier transform of f is just the sum over Fourier transform of phi s. And now we know that the support of the Fourier transform of f is supported on the union of those tubes. And we know that the tubes pointing in direction gamma prime t, so the union of them pointing in direction, that's like the union of those tubes. So now this becomes, the support is like very close to a cone over gamma prime t. And now this becomes some function with Fourier transform supported on some curved object. And that is exactly the object of study in restriction theory. And this is how it's related. One could use restriction theory to study projection theorems. And the proof uses the Bourgain-Demeter-Guth decoupling we have seen before. And this restricted projection theorem has applications to homogeneous dynamics. Yeah, that's a good point. So I lied a little bit, and you caught it. So when I say this is supported on curved object, it's true only at the high frequency part, because the tube centered at the origin, because phi s is just a smooth bound function. The Fourier transform has the essential support centered at the origin. So the tubes are all centered at the origin, and near the origin is like they all intersect. So it's somewhat like the overlap is more, and it's harder to explore the curvature. So in order to do the proof rigorously, then one need to decompose according to high frequency and low frequency. That's where the word high-low coming from. But at least I hope you can see that the union of those Fourier support is indeed like looks similar to neighborhood of a cone. That inspires us to apply restriction theory. So this the restricted projection theorem we have seen has applications in homogeneous dynamics and some number theory problem. So that's the first part of discussion on restriction on projection theory. That is, let me try to go back to the theorem. That is, so we consider the set some curve in the Grassmannian that one can imagine it has lots of curvature because it comes from consecutive derivatives of some of moment curve. So this is the observation is that if lambda is so-called curved enough, where there is one need to define what it means to be curved enough. Then we expect to have a very good projection estimate. And this is basically the best we can hope for. Although this is, this theorem is too restricted in the sense that it requires the subspace to be spanned by consecutive derivatives of some non-degenerate curves. But the kind of curve in Grassmannian could be way more arbitrary than this. For example, one could ask what happens if we don't take consecutive derivatives. We just take two curves, gamma 1 and gamma 2, assume that they are, let's say they are generic. We can also say that, let's say they are polynomial curves. Then what do we know? Do we still have this kind of best possible projection estimate? It's not clear, and it's, so yeah, this could be a nice problem to think about, and it's not clear if this high-low method would give the solution. So now let's move to the second topic. What if the lambda is not curved enough? So if this lambda, let's say it's a curve in the Grassmannian, I would say quote lacks curvature, which needs to be defined. But when it lacks curvature, then there would be some kind of obstructions, just as the example of a line and a plane that's normal, orthogonal to a line, that's one type of obstruction. But then suppose E is away from any obstruction. So here we are imposing additional assumption on E, depending on the set of subspaces we are considering. Then could we still expect to have a good estimate? So the Kakeya conjecture is a special case of this kind of discussion. So the connection is not very hard. So line segments in Rn can be parametrized. So most of the line segments in this can be parametrized by, let's say, A and B in the unit cube in Rn minus 1. So suppose we have a subset in the unit cube in R2 times n minus 1. So this is our set E. And each point corresponds to a line L. So each point AB corresponds to a line LAB. Then this K is going to be the union of those line segments parametrized by the points in E. So yeah, so this is LAB, start from the point A0 and pointing in direction B, 1. So how is this, so essentially Kakeya conjecture asks to estimate the dimension of sets of this form, and how is this related to restrictive projection? So now we can write down the explicit curve in the Grassmannian, the set of n-1 dimensional space in R2 n-1. It is just Vt is the span of 1, 0, 0, 0, T, 0, 0, and then we move to 1 right and T to the right. So this is not that important. I'm just writing it in n-1 subspace. The projection PT is just defined as follows. It's very easy to describe. It's just A comma B maps to A plus B times T. So this is the restricted projection. So here I'm writing it in this form just to try to convince you that this is indeed a curve that somehow lacks curvature. And then suppose this is a set, our set E. The projection image PT of E are the projection images are those blue points, and this equals to Now here on the right-hand side, we have K to be a union of lines in so the projection image is just going to be the slice of the union of lines with hyperplane with horizontal hyperplane of height t. So here we slice it with 3 points. They are equal. This is just because recall that the line LAB is parameterized by a comma 0 plus b comma 1 times t. So I hope this at least says something about the projection image is related to the size of the slice of the union of lines with horizontal hyperplane. So by Fubini, in order to show that union of lines has large dimension, we could just say that for a typical slice, this slice has large dimension, which corresponds to for a typical projection, the projection image is large. So what are the obstructions? Here is just one of the obstructions. So this is just the same as what we discussed last time. So for union of lines problem, the obstructions are just lines or tubes that's concentrated in a smaller, for example, in R3 are concentrated in a smaller box. So here I'm just drawing, instead of a general box, I'm just drawing a plane. Then for union of lines problem, the obstruction is when its lines are concentrated in a plane, and this can be translated to E contained in some two-plane W. For example, this is an obstruction. When E is this set, so equals to alpha 0 and beta 0, then for any t, so E here in this example has dimension 2, but for any t, pt of E is just R times has dimension 1. So this is an obstruction because for this example, we do not have a very interesting projection estimate. And so the Kakeya assumption is one way to rule out this obstruction. So it says that it adds the additional assumption on E, saying that the projection to the second coordinate is the unit cube. And then one can translate the Kakeya set conjecture to be for, suppose E satisfies the Kakeya assumption, then for almost every T, the projection image has 4 Hausdorff dimension. And so what Josh and I proved can be also translated that into this following form. Suppose E is subset of the unit cube in R4, and it is away from any obstruction. So this needs to be quantified. And the way to quantify it is just we should translate what it means for Kakeya sets, for sets satisfies Wolff axiom to be away from any obstructions. Then for almost every T, the Hausdorff dimension of the projection image is the minimum of the Hausdorff dimension of E and 2. So in particular, this term will correspond to the set satisfying the Kasta-Wolff axiom, and this term will correspond to the set satisfying the Frossman-Wolff axiom. Okay. So the point is just trying to translate what we have discussed so far about Kakeya sets into the more general framework about restricted projection. And as you can see that this is a very particular curve with obstructions. There are many other possible curves in Grassmannian that could contain obstructions. And what are the corresponding assumptions we should add to have some good estimate? So I'm just trying to convince you that this we only know a very small part in a very small dimension of the problem. Are there any questions? So in the end, so previously we talked about how restriction theory could help with projection theorems. And we also talked about how Kakeya set conjecture is a special case of the projection theorem. And for the last topic, we are going to say how projection theorems can be applied to study Stein's restriction conjecture. So there is this Furstenberg set conjecture in the plane, which is more general than the Kakeya conjecture. Well, here is only in the plane, but one could also ask Furstenberg set conjecture in all dimensions. So before I move on to this topic, let me just point out that here, when I say obstruction, meaning that E contained in some two-plane of this form, such obstruction only exists when dimension is greater or equal than 3. And this also explains why suddenly the Kakeya set conjecture is much harder in dimension n greater or equal than 3, because when n equals to 2, there is no obstruction. Okay, so, but still, when dimension n equals to 2, we could still ask a difficult and interesting question, that is the Furstenberg set conjecture. So the Kakeya sets, or what the type of sets we have studied previously, are union of lines. So for Furstenberg set conjecture, we ask, what if we don't take union of lines, but we only take, say, union of subsets of lines? So here is the setup. So since we have studied how sets can be parameterized by points, so now suppose E is a subset of R2, then it parameterizes a set of lines in R2. And suppose the set of E has Hausdorff dimension T. For any point AB in E, so LAB is the line parameterized by AB, and let YLAB, we call it shading, be a subset that has Hausdorff dimension S. So this just means a subset of the line. And then we consider the union of those subsets of lines. And we ask, what is the Hausdorff dimension of the union of subsets of lines? So this is the Furstenberg set conjecture in R2. And since we only have a subset of lines, so we cannot expect the bound to be as good as before. But here is the conjecture based on some lattice example. And this conjecture was proved by, so first the sticky case proved by opponent Schmerkin, and then very soon after the general case was proved by Kevin Ren and myself. So this more general version of like this Furstenberg set problem is more general than the Kakeya problem, but why do we care about this more general setting? Well, there is, so I hope, let's go back to this wave packet decomposition. Previously, we discussed how restriction conjecture is related to the Kakeya conjecture via the wave packet decomposition. So let's say it. So F is a function with Fourier transform supported on the paraboloid, and we said that the wave packet decomposition says that F can be decomposed into sum over wave packets that support on those long tubes. So when we want to estimate the LP norm of F, as we can see that there are parts that overlap a lot, and there are parts that don't interact with other things. So we expect F to be small here, and F might be big here or might not, depending on the oscillation. So this means that for the Kakeya set problem, we estimate union of tubes, meaning that we put the same attention on all the points along the tube. But in reality, when we want to estimate the LP norm of F, we should concentrate on the points on the tube where there are a lot of other tubes passing through it. So this is where it's more natural to consider subset of tubes instead of the whole tube. So that is how Furstenberg's set conjecture is relevant. And indeed, we were able to apply this on the result and apply it to restriction conjecture in R3 and obtain some partial progress on Stein's restriction conjecture in R3. It's maybe the interesting thing about this exponent is that via the same implication that Stein's restriction conjecture implies the Kakeya set conjecture, this implies Wolff's hairbrush bound, meaning that any Kakeya set in R3 has Hausdorff dimension greater or equal than 5 halves, which is the previous result that is very hard to improve. So I guess hopefully I've convinced you that the two fields are closely related and development in one would help with the other and vice versa. I will stop here. Thank you. You mean for Furstenberg? Oh.
Yeah,
I think the story I heard is that he posted this conjecture in an unpublished note, that when he was thinking of those his other famous conjecture as about intersections and times 2 times 3. So I don't know what he had in mind. So yes, maybe previously he had some vision of how this Furstenberg set conjecture is related to his splicing conjecture. Or say that if you have two sets that's either times 2 invariant and times 3 invariant, and then you take the product and then you splice with any line that's not orthogonal or horizontal, you expect it to have a very small dimension. And maybe that was what he was thinking.
Times 2 times 3. One application.
That's a good question because so it comes from A comma 0. In reality, I should say that this is the lines does not necessarily need to intersect this two plane, this plane, but any subset of the line is good. Any line segment is good. So A is the point when it hit. So A is where the line hit this horizontal hyperplane, and B comma 1 is just the direction. Oh yeah, so yes, so each AB is a point in E, right? And the assumption is that E has Hausdorff dimension T greater than 0.
Right, but you didn't say, you didn't say that
Oh, no. So no, AB is a point in E. So this is F and this is E. Are you thinking?
Right, but so LAB
is a line
parameterized by AB.
Yes.
But you have not lines on the line.
No, not. So one is in the parameter space and one is in the space of lines. So they are completely disjoint. Like they don't lie in the same space.
LAB is given by the same formula.
Yes.
Oh, it's not an arbitrary line parameter, but it means that line.
Yes, it's this line. Sorry, I was not clear. I think let me try to describe it. I think some of this previously, one could imagine that starting from the techniques of this Furstenberg set in R2, you could say, okay, let's try to do something in R3 to study the Kakeya set problem. But this turned out to be too technical, like very technical if you want to incorporate all parameters, like if you want to quantify how non-concentration it is. And then it turns out that the Wolf axiom is a much simpler sort of model or subset. And so I would say that this point of view, together with the Wolf axioms, that the other point of view for lines that people have studied, I think the two of them together helps. If just this point of view, it will be too technical or too difficult. But it helps in the sense that we could try to imagine the tools in like when we studied this. So first sticky and then general, and also organize things, and in also this multi-scale decomposition. They are like analog ideas. That's a good, I think, so I think so this Heidel method was inspired by the local smoothing result. So you might say that, when the studied local smoothing inspires us to study this restricted projection, then because to study higher dimensional local smoothing problem, you also have to overcome some Kakeya type problems. So I think, yes, it would be helpful. I'm just trying to say that things go in two directions. Yes, so that's why I didn't say two ends here. So this is so this Furstenberg set conjecture requires the Hausdorff dimension of the subset equals to S, and the bound depends on S. So previously we made some conjecture that's even stronger than the Furstenberg conjecture, that only requires an epsilon dimension, but the S is like some sort of Minkowski dimension. And that one we proved in 2 dimensions, and Alex Cohen found a counterexample in higher dimensions. And I should also say that it's the 2-dimensional stronger version of the Furstenberg set conjecture that has application for the restriction conjecture in R3. So yeah, this is becoming maybe too technical. That's a good question. No, I don't think so, because in two-dimensional first restriction conjecture is proved long time ago, but this one is only proved a couple of years ago.